Now, I would like to introduce our wonderful speaker, Dr.Jiawei Lu. Today, he will share his research about joint freeway traffic state and queue profile estimation using heterogeneous data sources, the subtitle, Differentiable Programming Reformulation on a Layered Computational Graph. Jiawei Lu is a postdoctoral scholar at the School of Sustainable Engineering and the Built Environment in Arizona State University. His research interests include traffic simulation, combinatorial optimization, and adoption of machine techniques in solving real-life transportation problems. He is leading some open source projects, including OSM2GMNs, which is a Python library for creating multimodal transportation networks from OpenStreetMap. So with all that said, now let's welcome him to start the presentation. Jiawei, now the floor is yours.
Oh, thank you. It's very nice to be here and share our research in this talk. My name is Jiawei Lu. I'm a postdoc working with Dr. Zhou at Arizona State University. So in today's presentation, in today's talk, I'm gonna show our recent research on freeway traffic state estimation and the queue profile estimation. So this traffic state estimation and the queue profile estimation are actually very classic problems. But in our work, we're trying to solve these classic problems with new techniques. In this presentation, I'm gonna cover these 6 parts, starting from introduction, then problem statement, then corridor level traffic system dynamics, followed by our methodology. Then we introduce computational graph. Finally, is numerical experiments. So we start with introduction. Here we introduce what is traffic state estimation and why do we need that. Due to limited budget, we can only install a limited number of traffic detectors in our transportation system. From this limited number of detectors, we can only obtain partial observations of our system. But if we want to design effective traffic control plans or strategies, it's better to have full observation of our entire traffic system, transportation system. So what is so that is what traffic state estimation does. We use partial observations from traffic detectors and try to estimate or try to infer the whole, the complete state of the whole transportation system. In this work, we actually focus on two states. One is classical traffic state estimation to estimate like traffic parameters such as flow, volume, density, and speed. So this is traffic state estimation. So I use this figure here based on these partial observations. We have GPS observation. We have observation from loop detectors. This is partial observation. And what we are trying to do is we are trying to estimate the QKV, volume, density, and speed on the whole space and the time region. So this is the expected results. Based on this complete traffic state estimation, we can better design traffic control strategies. This is the first one. Another one is we also try to estimate the queue profile. So compared to this detailed traffic state, queue profile do not care about the detailed like speed value or density value on a specific point. What we are caring about is the whole queue profile, like time-dependent queue length. This is extremely useful in traffic signal design on arterial roads. On freeway, it's very useful for like rapid metering control. So in this work, we are trying to combine these two things together and propose an integrated model to solve these two problems simultaneously. In the following two slides, I will briefly introduce the existing study in the literature. So for the first one, the traffic state estimation, we have two classes of methods in the literature. The first one is model-driven method. The second one is data-driven or string data-driven method. The major difference between these two classes is whether we incorporate or whether we include traffic flow models in our methodology or in our own method. In our work, we focus on model-driven methods. The reason is if we incorporate traffic flow models, analytical traffic flow models in our own methodology, that may like increase the reliability of our estimation result, especially in some points without good observation or the data quality is poor. So for data-driven methods, there are three major components. The first one is what kind of traffic flow models we are going to use in our model. So the most common one is continuous flow models. For example, the first order LWR model is the most commonly used in the literature. I want to highlight in this LWR model, we have three sets of equations. I want to highlight the partial differential equation here. The partial differential equation is used to describe traffic flow dynamics, but since it is described or since it is expressed by partial differential equations, that brings some difficulty when we're trying to solve model including such partial differential equations. So in the literature, what we do is we do linear approximation. We use a set of linear functions or linear equations to approximate the original partial differential equations. For example, CTM model. CTM model is the first order approximation of the original LWR model. This is the first component. The second component is estimation model. To estimate the traffic state or Q profile, there are two types of method. One is to formulate the estimation problem as an optimization problem, or we can model the estimation problem as an online filtering problem. So for the first class, the optimization model, typically we use nonlinear programming model or mixed integer linear programming model. But if we the first class of the optimization model suffer from scalability model, since if we are dealing with large scale instance or large scale problems, these two types of models typically have very high complexity. It may take like a couple hours to get a feasible solution from that model. And in terms of the second type is we call that filtering method, like Kalman filtering or particle filtering. This method is compared to the first class. This method is easier or is more efficient to get a solution, but it suffers from the convergence issue. If the transportation problem, if the target problem is not completely observable, that may have the convergence issue. The final result or final solution may not be converged very well. So this is the second module, and the third part is the underlying. We call it underlying traffic state representation scheme. So we want to estimate traffic state, or we want to estimate Q profile, but in which form we represent this state, in which form we are trying to model traffic profile. So in the literature, most study use discretization based scheme. I will introduce the traffic state representation scheme in detail in the following slides. But I just briefly mentioned that we have discretization based and the continuous based scheme in the literature. So, this is the TSE traffic state estimation, and the second problem we are trying to address is Q profile estimation. So, as mentioned, this is very useful or very important in arterial street management. Since if we want to design effective traffic signal timing, the time have a good knowledge on time varying Q length is very, very important. So we have lots of study on QPE, on Q profile estimation on arterial street, but the QPE on freeways received relatively less attention. Okay, so I briefly introduced what we have in the literature. I list the 4 challenges here, which serve as the major motivation of our work. The first challenge is these 2 problems are typically performed separately in the literature. So let me answer the question. So why it seems we are trying to combine, or it seems we are trying to incorporate these 2 models into one. So why do we need to do so? The advantage or the benefits of combining these 2 problems into one model is, since this TSE problem can provide the results from TSE can provide a detailed traffic states on target corridor, on target arterial street. That can provide like local reference or local observation to the QPE model. So if we compare these 2 modules, two problems, QPE is kind of from high level, and the TSE is from relatively low level. So this low level module can provide local observations or local inference to the upper level. So consequently, this upper level can provide a global observation to help stabilize local estimations, or local inference. So that's our motivation. Why are we trying to combine these 2 problems in one model? This challenge 1, and for challenge 2, as we mentioned in the literature review part, Q profile estimation on freeways received limited attention. We do have some works on freeway, but the total number of papers or studies are still relatively limited. And for second one, the widely used discretization-based traffic state representation schemes break state differentiability. So I use this figure, this simple figure to show to explain what does that mean. So if we want to estimate state on a freeway corridor on arterial street, this is our target system. So since the time and the space domain are both continuous, so what we do in the literature is we have this time x and space x. We have a space-time domain, space and time region. Since these 2 are both continuous, we will do the discretization. Like for time, we have like 5 minutes interval, and for space we have 10 meters. So we can do the discretization and build this we call this grid, and we build, for example, we are going to estimate the density. We have K here, and we will build an independent variable for each grid. So after doing the discretization, originally the traffic state are differentiable, are continuous. But if we do the discretization, this variable with another one, that one may be Ki plus 1 t. These 2 variables are completely independent. So that breaks the differentiability of traffic state. So if we remember the partial differential equations in the LWL model, if we do the discretization, we cannot directly adopt the partial differential equations in many traffic flow models. So this is the third challenge. The final challenge is limited. Limited to small or medium scale applications due to high problem complexity. As I mentioned before, we usually build a nonlinear programming model or mixed integer linear programming model to solve state estimation problems. That's from scalability. The model will become extremely complex when we deal with large scale problems. So these are the 4 challenges, and these challenges motivate our work in this presentation. Okay, so this slide will introduce we have the problem statement. We introduce what we are going to do and what's the input and what's the output of our estimation model. So the final objective is we systematically estimate traffic states and Q profiles by utilizing rich observations from different types of traffic detectors while properly handling potential inconsistencies between them and satisfying flow dynamics represented by traffic flow models. I highlight some words here, some keywords here. One is state traffic state. We're going to estimate traffic state, and one is Q profile. We're also trying to we're trying to estimate these two at the same time. So the data we use is rich observations from different detectors. And we also incorporate the information from traffic flow model since we are focusing on model-driven method. We want to minimize. We want to minimize the inconsistency between these different modules since we incorporate lots of modules, lots of data source, lots of knowledge from observations and from traffic flow models. We want to the expected output, the expected outcome is the estimated states have the minimal inconsistency between what we observed from traffic detector and what we have from the information from traffic flow models. So this is the objective. So input I list for traditional traffic detectors as examples, but it's not limited to this. For we can incorporate other new data sources. I only listed this for the illustrating purpose: loop detectors, GPS, and Bluetooth and video detector. So the output is since we are addressing these two problems, the output is the time varying traffic states. Such as volume, speed, and density. And another output is time varying Q file. I have these two figure here. This is expected results, the outcome of the state estimation problem, and this one is the result, the expected results of the Q profile problem. So if we comparing these two, this will provide detailed information on QKB. This will provide like coarse, high level time varying Q length. Okay, so we mentioned one challenge in our in the previous slides. To show the issue if we use discretization-based state representation scheme. So I put this figure here. This is discretization-based. We have the continuity issue. We have the differentiability issue. So in our work, instead of doing discretization on traffic states on the space and the time domain, what we are trying to do is we want to directly estimate a continuous function of each variable of interest. So, for example, this is the density. For example, density or speed. We do not do the discretization. We want to construct a continuous function. The function, the input, the argument of that function is x and t, and this is a continuous function. If we for calibrated of estimated function, if we have x and t, we put the x and t into that continuous function. The output of the output of that function is estimated value of that traffic state. So I will have some examples in the following slide. So the major difference is we do not build independent variables on each grid. Instead, if we look at this figure, we are trying to directly construct a function, a continuous function for each state. So this is for the traffic state estimation for like a QKV, flow volume density speed. Since we're also addressing the Q profile estimation problem, this is a low level traffic state representation. The high level Q profile estimation scheme. From the high level, we treat the traffic system, the corridor, as a queuing system. So for queuing system, there are two major parameters or two major variables. One is the input, one is the arrival rate, another is the service rate. So we also do not do the discretization. We also try to directly estimate or infer the continuous arrival function and the service function. So for transportation system, the service function is a discharge rate function. So we have this arrival function lambda t here and the discharge rate function mu t here. Since the other statistics, for example, Q length, for example, waiting time, travel time, time-dependent travel time, can be derived from these two basic functions. So this figure here lists, since we have this output, the input are very intuitive and clear, but the output we want to highlight. So in which form we are going to represent, or in which form we are going to model this output. So this is the state representation scheme in our work. So based on this state representation scheme, we want to provide the variables of functions. We summarize the variables of functions we're going to estimate in our problem. So since we are focusing on a model-driven method, so we'll also have, for example, the fundamental diagram. We have free flow speed. We have KGM. These are also parameters. So these parameters are also will also be estimated in our model. These parameters are not predetermined or pre-calibrated. So this is the parameters. This phi is a parameter from traffic flow models we use in our final model. And we have functions. We have four functions which can be classified into two groups. One group is for high level Q profile estimation. This is lambda t, this is mu t, a system-wide arrival rate function, and mu t, system-wide discharge rate function. And also we want to calibrate, or we want to estimate the other two functions is for state estimation. One is traffic density distribution function. So the input is x. The two arguments are x and t. And also we have function g here for traffic state or for traffic speed distribution function. Since for a specific point, traffic volume equals density times speed. So we do not need a set function for volume. we use the f times g, we can get the volume function. So these are the four set of functions to be calibrated, and this is the parameter to be estimated. Okay, so based on, since we are using a totally innovative state representation function, so we may bring some key, before diving into our detailed modeling process, we have some key functions to answer. The first question is, since we are going to construct functions, and that functions is, we cannot, is uncontrollable. We do not know what does this function look like. So the first question is how to choose a proper form for each function to be calibrated. We have different forms. We have polynomial functions. We have sine, we have log. We have exponential functions. So how do we know which function should best to our system of interest? This is the question one. Another question two is, so if we build a independent variable for each grade, it's easier to combine, to compare the estimated value or the observed value. But if we working on functions to how to measure the inconsistency on these functions with observations, with traffic flows. And the third one is how our representation scheme can help handle partial differential equations in traffic flow models. I remember I have a function here. Oh, okay, it's right here. Okay, so these are the three functions. For the first question, I will answer that in the following slides. Let's assume we can select a proper function form, a proper form for each function for now. Assume we have a function. For example, we choose a sine function, and since the function form is there, what we are going to do is we want to calibrate, or we want to estimate the parameters of that function instead of the function itself. We want to estimate the function, the parameters of that function. If I go to the function, sorry, I didn't put that in the correct page. So for example, for this f function, we have this is a very simple example I listed here for illustration purpose. So for example, we choose this form. This is a f function with argument x and t. So the function itself is ax plus bt plus c. If we choose that form, and if we believe that form is correct, so what we are going to do, what we need to do is we want to calibrate this a and b and c instead of the function itself. Okay. So now we do not answer how to choose the function forms for now. Now, as we assume we have function forms. So this is the question one. For question two, we have that function. The function across the space and the time domain. So to measure the inconsistency between our estimations and observations, we choose some sample points, and we measure the inconsistency, or we calculate some important statistics on these sample points, or we can call them control points. So for that continuous space-time domain, we can choose any control point if you think they are important. For example, I evenly choose this point on our space and time domain, and we only calculate the consistency, the inconsistency, the errors estimation as on these sampling points or on these control points. I use this xt here. Xt are XT is a vectorized form of our sample points. So if we this is the f function with parameters theta to be calibrated. So if we plug in this substitute this XT here, we can get estimated value K on these sampling points XT. So this K are actually a function. The K are actually a function of theta. Since this K is calculated from theta, so this K is a function of theta. Similarly, we have V from function G with parameter phi, and since Q equals K times V, we also have Q here on this sample points, on this control points. This QKV are the functions of theta and phi. So that's how we address the second question. For the third question is how to handle partial differential equations on in traffic flow models. So instead of doing a linear approximation, since we are working on function-based approach, for example, as I mentioned, we have this function form for f, and since we already have the analytical expression of these functions, so analytically derive the partial differential terms is very intuitive or very easy. For this function, if we take the derivative of function f with respect to x, then it's a is parameter a, and if we take the derivative of function f to t, is b. So as long as we have a function form of traffic state of function g and the function f and the function g, we can analytically derive the partial differential terms very easily. At least we can do so. So for complex function, for example, this function f is very, very complex. So that may need some efforts to obtain the derivative functions, but theoretically we can do so. So these partial differential functions are also analytical functions with parameter theta and phi. So I list this. I use this example here and put our formal equations here. So this KT are also a function of theta and phi. So these are three key questions to answer before going to our model. So let's go back. Okay, so we have introduced sorry. We have introduced our problem statement, and we have introduced the foundation of our model. So that is how we represent how we model our trap state. Now we are going to introduce our model. Since we are addressing two problems at the same time, so we have Q profile estimation, high level Q profile estimation, and the lower level traffic state estimation. We are going to build a model-driven model. So in lower level traffic state estimation level, we have well-defined like fundamental diagram. We have well-defined like a 3D data model. We have lots of model. But on the high level, in the high level Q profile estimation, we also need to we also need analytical models to stabilize or to make our estimation reliable. So in these two slides, we are going to derive, or we're going to propose analytical high level model for for Q profile estimation. So we treat the state of interest as a Q system. So if we go to this figure here, this figure is a corridor. We have ramps, on ramps and off ramps. So the two major input of this system is arrival rate and the service rate, and the other statistics can be derived from these two variables. So we starting from this arrival rate. We're starting from this arrival rate and discharge rate, this lambda t and mu t, which are the two functions we are going to calibrate in our model. So we want to, since these two, especially for the virtual arrival, it's very hard to observe in real life. So what we are trying to do is we derive observable traffic measures from this lambda t and mu t, this arrival rate, this departure rate. So what we can observe is we can observe like time-dependent travel time. Time-dependent travel time from our system. We can observe time-dependent Q length from our system. So we want to derive analytical Q length function and analytical travel time function from these two basic functions. This is arrival rate, and this is from a Q system. This is arrival rate. This is a departure rate, and this is the Q length for that period. Starting from T0, we have a Q starting from, and starting from T3 until T3. Starting from T2, the Q start to dissipate, and at T3, the Q length equal to 0. So this is the Q length figure, and this is the cumulative arrival and departure curve. So this I grabbed some equations from our paper. So let me quickly go through them. So for this mu t, we use Taylor series expansion, Taylor series approximation, the second order Taylor series expansion at T1. So we have this second order approximation. Since at T1 we have the first order is 0, so we have this function for mu t. Actually, we are using. So speaking of choosing which form for each function, for this high level, we are choosing a polynomial form, since we are using Taylor series approximation for this lambda t and mu t. So for second order approximation, we have the form of this mu. So if we choose this form, now the parameter we are going to estimate is this mu at T1, and this gamma here, and this T1 here. These three parameters. If we choose it from these three parameters are the variables we are going to estimate. So this is the mu t function, and this party is the net flow, is the mu lambda t minus mu t. So if we look at this figure, since at T1 and T2, inflow equals outflow, so the net flow should be 0. So since this is second order function, and we also approximate this net flow as a second order function, it has two groups. One is T0 and T2. So we have this kind of form for this pi. For this QT is the integral of pi t from T0 to T. We have these derivations, and with observation that at T3 Q equals to 0, and we have the relationship between this T1, T0, T2, and T3, and finally we substitute this T2 into that function. We can get a very elegant form of of Q. This is Q length. So for Q length we have gamma, we have T0, T3. So this equation derivation is very tedious. I just quickly go through here. So starting from this starting from this lambda and mu, we can also get an analytical function of Qt. This is a Qt here, and we also further derive what we call WT. WT is waiting time. If we plus this TF here, so waiting time plus free flow travel time is the travel time. So I use this table here to summarize what we derived in the previous slides, starting from lambda t and the mu t. All the way we derive analytical functions of travel time, occurrence of travel delay. Why we want to derive this is since if we have this travel time function here with some unknown parameters, for example TF, for example TF and for example T0 from this basic function. Since we have so as long as we have these analytical functions of this observable traffic measurement, we can use observed travel time to calibrate that function, like least square method to by calculate this function, so that we can get estimated like TF, estimated T0, T3 here, and after calibration, after estimation, we can get with these all parameters to be with all these parameters determined, we can have a complete estimated function of like TT of mu t. So this is the high level derivation, since we do not have we are trying to propose suitable traffic flow models for high level Q profile estimation. So these are all the derivations based on grid Q perspective. Now we go back to we'll go back to these slides again. So we use this polynomial function forms for this lambda t and mu t. Since these two parameters or these two functions are one dimension functions, is relatively easy. But for these two functions, it's two dimensional. We have two arguments, x and t. It's not that easy to even to express or even to approximate the two functions very with polynomial functions. It's very hard to do so. In our numerical experiment, we will introduce what we use for these two functions. Now we still assume these two functions, the form of these two functions is determined, and what we need to do is to calibrate the unknown parameters of these two functions. Okay, so after introducing the high level Fourier Q model, we now going to introduce how do we measure the inconsistency based on our in our model or based on our state representation scheme. So we split this into two parts. One part is for the QPE. How do we measure the inconsistencies in QPE, and how do we measure inconsistencies in TSE? So this equation actually explain how we incorporate, how we combine these two models, two problems into one model. So as we mentioned, this Q is the simply points on this low level state estimation problem is on this side, and this mu t, this mu t is the discharge rate on the high level. So if we want to put this problem together, we want to make sure the results or estimation results from these two modules are consistent. So speaking of this discharge rate right here, so we want, if we plug this t here, is the discharge rate of is the flow on this downstream on this downstream with a red line here at the downstream, and this Q are controlling points of all within our space-time regime. So we use a coefficient matrix, the W here. We put the weight of other control points at 0 and only put one for the control points in downstream. So this is the estimated volume from the upper level, and this is the estimated volume from the lower level. We want to make sure these two are consistent. So we derive these inconsistencies between these two models first. So this is the part one. And for the observation, since we have analytical function from Q length, from the travel time, this travel time can be obtained from the Bluetooth detector, from the GPS detector. So for example, we have observations, travel time observations on T prime, and we substitute this T prime into our analytical TD function, and this will give us estimated travel time on T prime. We compare that with our TT tutor observed travel time, and we want to minimize our estimated travel time and observed travel time. We calculate the inconsistency terms here. So these are the inconsistency. We have more inconsistency terms in the following slide. So for the fundamental diagram, this is the triangular fundamental diagram equation. So we want to make sure the estimations of all sampling points of all control points satisfy traffic flow fundamental diagram. So we substituted our sampling points, the K and Q on our sampling points on the other equation, and we compare this Q and how do you see the output of the fundamental diagram? This is the Q estimate. We compare these two, and we want to this is the inconsistencies from the fundamental diagram, and we also want to minimize these terms to make sure the fundamental diagram holds on our sample points. We also have flow conservation flaw. So as mentioned, we can easily derive the partial differential equations based on our function-based representation scheme. So we can instead of doing like a linear approximation, we can analytically have this function and analytically express this Q, X, and KT, and calculate the inconsistent terms. Like a straight detector, we have a forward wave and the backward. We want to make sure the state on this forward wave or backward wave are the same. So we calculate these terms based on straight detector models. We only list some models in this slide for the illustration. But if we are interested in like a higher order model, we can also incorporate that models in our framework. So we introduce how to incorporate traffic flow models, and now we introduce how to incorporate our loop detector data. So based on these sampling points, for example, we have the C tutor here as a count observation from loop detectors. So since we have this Q estimation on these controlling points, this estimated count on that time interval can be weighted linearly weighted from our Q estimation. So I listed this function here. This is the Q, our Q volume estimation of our control points, and we times coefficient W here to make sure this coefficient W, the elements in WT, all other control points have 0, but this ABCD have this like half, 1, 1, 1, and half in this coefficient matrix. So we get the estimated value on this time interval from A to E, and we compare this C with tutor. So we use tutor here minus WQ here to calculate the inconsistency between estimations and our counter observations. So we also have different kinds of observation, for example, speed from GPS data, and how to calculate it, and based on the FIFO condition, how do we calculate the inconsistency? So I will not go through that in detail. Then if we have video detect data, how do we utilize their density, use speed to calculate the inconsistency terms? So let me quickly skip that. So this is the final model. So we have three sets of constraints. One is state estimation of sample points. Another is inconsistent constraints calculated on these sampling points. So these are the three set of questions. The objective function is we try to minimize these objective functions. Let me see. Maybe I need to speed up. So essentially, this unconstrained problem. So since all these equations, all these constraints are used to calculate these inconsistencies. So this objective function is actually a composite function of these constraints. So this is a nonlinear unconstrained problem. If we minimize that, we will minimize this objective function. We want to actually we're minimizing the inconsistency between observations and our estimations, and also with traffic flow models. So for this model, we can directly solve that in using nonlinear solver, for example, barrier, for example. But we have three challenges. One is scalar computation. In solver, we build each variable independently for each control point, not in a vectorized form. So this is the challenge one. Challenge two is, although we can analytically derive the derived functions of function f and g, but then you need some manual efforts. The final one is how to determine the function force. So we propose the computational graph approach for this. For the first challenge, since in computational graph we use a tensor to do the calculation. Tensor is actually a matrix or vector, so we are fully utilize the vectorized form to speed up the calculation. And in computational graph, we have automatic differentiation to calculate the partial differential terms. And finally, for this distribution function f and g. So I still didn't answer how to choose a proper form for these two functions. So here we introduce the computational graph. We're using fully connected neural network to approximate these two functions. The reason why we choose fully connected neural network is a feature of universal approximation. So we cast our model in this computational graph. The input is xt, and by parsing this function f and g, we can get the kv estimations, and we further calculate some inconsistency terms based on our previous equations, and finally we calculate total loss, which is the objective function of our optimization model, and we want to minimize this total loss. So this is a very if we cast our optimization model now, it's a very intuitive. This is a graph, and we want to minimize the total loss. So we have a forward and a backward process, forward and backward algorithm to minimize the total loss. So I was speaking that this is the training process forward or backward, and we also build a distributed version of our computational graph. So let's skip that. So this is a numerical experiment. So we choose three set of we choose three data set to demonstrate the efficiency, to demonstrate the performance of our model. So on the left hand side, these are the observations from real world data. On the right hand side is the estimation from our produced by our model. So these are speed observations. The redder the color is the lower speed is. So as we can see, the estimations are very close to its corresponding their corresponding observations. So this is one data set. Another data set is we choose a corridor from the PAM system. Actually, it's a freeway corridor in California. So we do the calibration, and this is also speed estimation for the other corridor. Since we do not have ground truth on speed, so this is our estimation. So I also choose the speed from PAM data. So we compare these two. We can clearly see the forward wave and the backward wave, and this propagation have been clearly reconstructed in our estimation. So this final figure shows the distributed version of our computational graph. This ground truth, this is centralized model produced by centralized model. This is produced by distributed version. So we can see this all very close to each other. Let me close this presentation by answering this 4 challenges. So for the first challenge, we do the integrated modeling. For the second challenge, we use we derive analytical Q derivations for high level for corridor level Q profile estimation. And for the third challenge, we use a special template of continuous function. And for the for the final challenge, we use the differentiable programming and computational graph to solve the computational issue. Okay, I think that's it. Since we do not have time, I think this presentation ends at 11. So originally I prepared these 2 slides. I think we do not have enough time. So that's it. That's all for my today's presentation. So thank you.
Thank you so much for your wonderful presentation, Jiawei.
Thank you.
It was a great time to have an insight about the importance of Q profile estimation, additional to TSE, and I think it was a numerical way to estimate unknown traffic state using various data and differentiable programming of continuous space-time distribution. So now the floor is open to the audience. Please unmute yourself to cast a question, or feel free to leave it on a chat box also, so that we can read it out for you.
Hi, Jiawei. Thanks for the interesting talk. Yeah, I have a couple of questions regarding the generability of the approach and how to evaluate them. The first one, I believe it is possible to have multiple models to satisfy all the constraints and the conditions from the sample points. And if so, how to choose one over the other if you find there could be multiple forms of those functions, and also possible multiple combinations of parameters that satisfy all the conditions, how to pick a good model from them.
Oh, okay, yeah. So in our work, instead of providing a detailed or specific application, what we are interested in is we want to provide an innovative modeling framework. So we want to provide this framework. We want to provide how we can model a TSE or QPE problem using space and time continuous function representation. But in terms of which model, which traffic flow model, for example, we use a triangular fundamental diagram in our implementation. For a specific model, you can choose your own model, or you can compare them by yourself. What we are doing in our work is we want to introduce this new modeling framework. So we do not introduce, or we do not encourage you to use a specific traffic flow model.
Do you think the solution is unique to for some of the problems you listed here? For example, the Q estimation.
Oh yeah, so that is a very good question. So if I go to this slide here, so these constraints, our linear constraints, are very easy. But in terms of objective function, we can say first we have a threat here, so it's already nonlinear. And if we incorporate like a fundamental diagram here, we have nonlinear function. So this objective function is hardly nonlinear, and I think it's hardly non-convex. So to solve this problem, to solve this non-convex problem to optimal is very, very difficult. So in our approach, in our experiment, we try to solve this model, to solve this nonlinear model, non-convex model in neutral invariant. We cannot get a feasible solution for that model. So we try to solve that in computational graph. But I have to say, even we use computational graph to solve that model, we still cannot guarantee the results we get is optimal solution. Yeah, so
that makes sense.
Yeah, we have a convergence curve. We stop our forward and backward algorithm until we see the convergence curve is stable. But even it is stable, we cannot guarantee it is a global optimal solution. That may be a saddle point or local like optimal. So that may have some that's a challenge.
Yeah, I actually have one comment on this for your consideration. I believe we can have different solutions from different locations of our interest, but to guarantee it is more, it can be generalized to more locations. I think we can try to evaluate model using other metrics. For example, if you have an analytical expression of the Q model, it will be interesting to see the distribution of the Q and see if it fits better, if one model can fits better than the other using the real world data from other locations. It's interesting. This year at TRV, I saw a poster presenting the Q distribution at an intersection or corridor, and they showed that it seems it's a long tail distribution, which might indicate some intrinsic nature of the Q that could be can be generalized to everywhere. So my point is, if we have different solutions of the Q estimation, we could possibly use those analytical forms to examine their distribution and find one that can fit better than the other. That's just one of my suggestions. I hope
I have,
could be of interest to you. Yeah.
Sorry,
please go ahead. Yes, okay, go ahead.
Hello, Jerry. Thanks for the presentation. Yeah, like actually related to his point now, since you're using the triangular fundamental diagram, and if you think like about the Niels model and the link transmission model, they have a formal definition of a Q, especially like if you see, like, for example, Professor Wenlong's Jing paper on Q and vacancy formulation. So a solution of that in a specific segment, we have a formal definition of Q from that model. So then actually the Q estimation from that, like if you estimate it based on that model, you already have a Q estimation. And actually that would be my comment. So why not assuming that, like since you are already assuming the triangular fundamental diagram, why not going to that formulation, which already has a formal Q definition?
Oh, you mean the first one? We have two parts. One is the Q profile estimation, and another TFTC. So you're interested in the Q profile estimation. So why we propose, why are we trying to derive these equations, given we already have some existing models on that, right?
Yeah. So then we're saying, like, if you think about the LWR model, you think about the triangular fundamental diagram, like there is one model which some people call the Niels model, some people call the link transmission model, which in itself is a triangular fundamental diagram. And at the same time, based on those equations of that model, or at least let's say that formulation, there is a Q definition. So then if you're able to estimate the traffic state based on that model, you by itself, or actually like commented, like a suggestion. So then you're already also estimating the Q. Yeah.
So that's a good point, and that's a good question, good suggestion. So in our work, instead of as I mentioned before, instead of interest in a specific model, what we are trying to do in our work is we propose a modeling framework. We're going to incorporate different models in our space and time continuous function representation scheme. So you can incorporate or you can choose any traffic flow models you are interested into our modeling framework. So that what we want to express, or that what we want to introduce. We're not introduce a specific traffic flow model. You can incorporate any model you're interested in our modeling platform. We want to highlight the space and time continuous representation scheme, and we want to highlight the computational graph computational power to solve the classical challenging problem. using new techniques.
And yeah, okay. So then, from that point of view, like how can we be sure that we don't have like negative solutions or above capacity solutions? Is there any? I think you mentioned a little bit related to that, but then is there any formal way, like can you have negative densities or negative flows or positive, like higher the capacity flows? How that can be ensured?
Yeah. I didn't mention that in my presentation in my talk, but I do have that issues in our implementations. So sometimes in order to get a very good objective function value, in order to get a very good like final optimal solution, some values in the flow density may be negative. Since the data quality may be poor, we have some noisy data that may result in like bad results, better estimation results. So one thing what I want to highlight here is that's the reason why we want to incorporate traffic flow models to stabilize estimation to minimize the possibility of that poor situations with like negative values. So this is one thing. Another thing is, in our implementations, we do find that issues and we do address that issues. For example, for negative values, we have for a specific figure, like for this k here, we do have like for example k hat here. This is the estimated k. That guy may be negative as this support value. So instead of using that k directly to calculate our objective function, we use this maximal k and 0 to calculate the final let's say q k hat prime. We use this function to calculate the final estimation. So for these operations, we have very good like function in TensorFlow in PyTorch. It's a ReLU function. It can help you to erase the negative part of estimation results. So yeah.
Thanks.
Yeah, so thank you for your comments.
Are there any more questions from audience? How do you have more comments?
No, I think if there are no more questions, we can call it a talk.
Yeah, I think we're a little bit out of time, so it's a good time to end our webinar. Thank you again, Jiawei, for your passionate presentation and being with us today. Also, thank you so much to all the audiences being with us. We look forward to see you again in the following webinars, and hopefully the webinar is going to be held bi-weekly on Friday if everything goes well. So I wish you all have a great weekend.
Sure. Thank you, Jiawei.
Thank
Yeah.
you, Jerry.
Thank you,
Jiawei. Thank you, Garyang.
Thank
you, everyone.